And welcome back, students. Let's go ahead and jump into our next exciting unit on programming. We're going to dive into the topic of polymorphism. So let's start with our first lesson, which is that of late binding. And this is going to be a little bit more of a theoretical lesson than some of our other ones, but nonetheless, it is an important one to go over. So getting started, there are three main mechanisms that constitute an object-oriented programming language. And we've already talked about two of them. There was encapsulation and inheritance. That's where we talked about like base classes and derived classes. We've kind of touched base on those already. However, there's a third one, which is polymorphism, which is what we're going to largely deal with in this chapter. Now, polymorphism refers to the ability to associate many meanings to one method name by the means of a special mechanism known as late binding or dynamic binding. So let's go ahead and start defining what polymorphism is. So if you recall, we used inheritance. And inheritance, it allowed us to define a base class and to define software for that base class. The software then can be used not only for the objects of the base class, but also for objects of any class derived from that base class. Now, what polymorphism does, it allows us to make changes in the method definition for the derived classes and to have those changes applied to the software written in the base class. Now, this typically will happen automatically in Java, but it's important to understand the process. So if you run into issues or anything like that, you need to troubleshoot, you understand the process of how polymorphism works so that way you can tackle those problems head on. Now, to help us better understand polymorphism, let's go ahead and look at an example. So here we're going to be talking about late binding. So suppose you're designing software for a graphics package that has classes for several kinds of figures, such as rectangles, circles, ovals, and so forth. Now, each figure might be an object of a different class. For example, the rectangle class might have an instance variable for height, width, and center point. Well, the circle class might have an instance variable for center point and radius. In a well-designed programming project, all these classes would be descendants of a single parent class called figure. Now, suppose you want to have a method that will draw a figure on the screen. Well, to draw a circle, you need different instructions from that of if you draw a rectangle. Obviously, a circle, you pretty much just need the center point and then the radius, and just have equidistant everywhere from that point. Rectangle, well, it's a little bit different. So each class needs to have a different method to draw its kind of figure. However, because the methods belong to the classes, they can all be called draw. If R is a rectangle object and C is a circle object, then R.draw and C.draw can be methods implemented with different codes. Now, obviously, this is nothing really kind of new to us. We kind of can figure this out, even just without having to have too much programming experience, because obviously a rectangle is a very different shape from a circle. But we are going to expand upon this concept just a little bit. Now, the parent class figure may have methods that can apply to all figures. For example, it may have a method called center that moves a figure to the center of the screen by erasing it and then redrawing it in the center of the screen. The method center of the class figure might use the method draw to redraw the figure in the center of the screen. Now, when you think of using the inherited method center with figures of the classes rectangle and circle, you might begin to see there's some complications, namely that a rectangle and circle aren't the same shape. So to make our point clear and a little bit more dramatic, let's suppose the class figure is already written and in use, and sometime later we decide to add a class for a brand new kind of figure. Let's say the triangle. So obviously the triangle can be derived of the class figure, so the method center will be inherited from the class figure and thus should apply to and perform correctly for all triangles. But there is a complication. The method center uses draw, and the method draw is different for each type of figure. If we recall, draw is defined within rectangle, it's defined within circle. But the method center, though, was defined within the class figure. Remember, draw is in each individual shape, whereas center is in the parent class, which means that the method center was compiled before we wrote the code for the method draw the class triangle. Now, when we invoke the method center with an object of the class triangle, we want the code for the method center to use a method that was not even defined when we compile the method center. Namely, we were looking at the method draw for that of the class triangle. See if it can be applied to other shapes as well. Now, can this technically work within Java? Making these new methods work work within these classes? Well, of course it has to, you know. And the nice thing about Java is that it does this automatically. We don't have to write any special code. You know, it's pretty much just going to be like a lot of what we've been doing. I would just go ahead and write my code for the figure class. I write my code for my individual shapes, and I just have to call those appropriate methods. All right, we don't need anything special after we define either the base class figure or the derived class triangle. You know, just like we did in the previous chapter, base class, derived class, you know, extends. Now, the situation we discussed for the method center in the derived class triangle works out as we want because Java uses a mechanism which is known as late binding or dynamic binding. Binding refers to the process of associating a method definition with that of a method invocation. If the method definition is associated with the method invocation when the code is compiled, that is known as early binding. So if it had been done the other way around rather than how we did in our example, that'd be early binding. However, if the method definition is associated with the method invocation and the method is invoked, which is at runtime, then that is called late binding or dynamic binding. Now, Java uses late binding for all methods except for in a few cases which will be discussed later on. So let's just see how late binding can work in the case of our method center. So recall that the method center was defined in the class figure and that the method definition of center included invocation of the method draw. If, contrary to fact, Java had used early binding, then when the code for the method center compiles, the invocation of the method draw would be bound to the currently available definition of draw, which is the one given in the figure. So whatever figure's definition of draw was, if let's say it was similar to that of a circle, that's what it used. And so when you go to try to draw a triangle, obviously it's going to try to draw something more like a circle rather than invoking. Because in early binding, if that's used, the method center is going to behave exactly the same as all derived classes of the class figure as it does for objects created using the class figure. Fortunately for us, Java uses late binding. So when center is invoked by an object of the class triangle, an invocation of draw, which is inside the method center, is therefore not bound to a definition of draw until the invocation actually takes place. So this is pretty key here because, you know, like we said, if we did it the other way around, it wouldn't be so beneficial, but because we can use invocation, we're using late binding. At this point in time, the runtime system knows the calling object is an instance of the class triangle, and so it uses the definition of draw given in the definition of the class triangle, even if the invocation of draw is inside the definition of the method center. So the method center behaves differently for an object of the class triangle than it would for an object that is just a plain old figure. With late binding, as in Java, things automatically work out the way you normally want them to. So it's pretty nice. Now note that in order for late binding to work, each object must somehow know the definition of each method that applies to that object. So when an object is created in a system using late binding, the description of the object must include either directly or indirectly a description of where the appropriate definition of each method is located. This additional overhead, this additional step of having to, whether it's documentation and stuff like that, is kind of the penalty you pay for the convenience of late binding. Late binding, very nice, but they do have a little bit more overhead on it. All right, and let's kind of wrap up here and just discuss how the late binding relates to our topic of polymorphism, because obviously that's what we're trying to learn, and we just spent a whole lesson talking about late binding. Well, the terms polymorphism and late binding are, for our intents purposes, essentially just different words for the same concept. The term polymorphism refers to the process of assigning multiple meanings to a method using late binding. Boom, that's it. Yeah, that's pretty much, if you look back at our first slide, that's almost exactly the same definition that I gave for that polymorphism. And that's it, folks. So I guess I will see you next time.